Welcome to the UGC lecture series. In this lecture series, we are talking about postgraduate courses, and here we are talking about the paper called data structures, and in this module we are going to talk about a very important data structures called the queue, and we are going to talk about the queue from the ADT perspective. We have already seen other data structures like list and stacks, which we also spoke about from the ADT perspective. So, these are the people involved in creating this particular module. And now let us look at the learning objectives of this module. Okay. So, the learning objectives of this module are basically to understand the concept of a queue, just like we did to understand the concept of a stack. Here we are talking about understanding the concept of a queue. Okay. Then we are going to look at the method for defining a queue. What are the basic requirements for defining a queue? And then we are looking at the different queue operations, just like we did. This is basically implementation independent, that is we are looking at it at the operations from an ADT viewpoint. Okay. Then we are going to look at some typical uses of queues. Just like stack was a very important data structures from the computing viewpoint, the queue is an equally important data structure from the computing viewpoint. And some of the basic keywords that we are going to talk about here is of course the queue and the queue ADT, and the principle on which queues are based, the FIFO principle. So, if you understand the FIFO principle, you have understood the concept of queues. Now, this queue FIFO principle is the same as a everyday queue. So, let us look at some examples of everyday queues. So, we are going to look at first some characters. These are characters that you often see in advertisements, and this is a typical example of a queue of those characters. Then you see, look at a long queue. This could be to enter into a ship, to enter into a plane, it could be for some purchase or some, this is a typical queue that you can have. You can also have in a traffic jam a queue of cars. So, these are some everyday examples of queues. Now, let us go a little further into how the understanding of the concept of queues. So, we talk about a queue as having an input and an output. Any list for that matter has an input and an output. But the queue, as we already spoke about, follows the first in first out policy. What does this mean? The first element that comes into the queue is the first element that leaves the queue. Okay. So, that is the concept of queue, and you see here that A has first entered the queue and A is the one that first leaves the queue. So, you have two ends to the queue. Here we will call it as input and output. Later on we will look at the technical terms of what these ends are called. Now, let us just look at some examples. You have a car coming, he pays and leaves. This is a typical toll station queue. Then you have check-in at the big bazaar, where customer comes, checks out and leaves. And this is more examples like printers, printer queue, office hours where you stand in the queue for a lot of things. So, these are typical examples of queues. Basically, these queues are for servicing, providing service. Now, let us go a little more detail into a queue. Now, this is the everyday queue that we have already seen, where you have a line of people standing. That is a typical example to get some service, like for example, it could be a bank counter to get some transaction done, to buy a ticket and so on, to check out, and which we have already seen. This is everyday queue. Now, let us look at the queue from a computer viewpoint. Okay. So, this is the computer queue. The meaning is that the queue from the computer viewpoint. So, here as I already told you, we have two specially designated ends called the front of the queue and the rear of the queue. And what is this front of the queue? Now, as we already told, in any data structure you have insertion and deletion. So, in a queue the insertion is done at a specially designated pointer called the rear, and the operation of insertion from the queue viewpoint is called end queue. Similarly, you remove or an element from a queue. Remember, queue is a restricted list. So, again you are removing or deleting an element, but from the queue viewpoint it is called DQ, and you do that deletion from the specially designated pointer called the front. So, this is a computer version of a queue. Now, again let us go a little more detail into what are the characteristics of a queue. So, it is an ordered list of homogeneous elements. What does homogeneous means? Homogeneous means all the elements of the queue are of the same type. It could be as simple as an integer, it could be as simple as a string, or it could be as complex as a record. But whatever it is, that structured record or something, but whatever it is, all the elements are of the same type. So, it is called homogeneous. This was true of stack also. Okay. Unlike a stack, which had only one end, either through which you inserted and deleted. Queues have two ends, which we have already seen in the previous slide. So, elements are added at one end and elements are deleted from the other end. Okay. So, that is the queue, and a queue is similar to a list. Okay. It is similar to a list, but items are added only at one end and removed from the other end, which is called the front. So, the element added first is always removed first, and that is why we say that the queue follows the first in first out policy, or in other words the FIFO policy. Now, let us look at some queue terminology. So, you have, as I already told you, a queue consists of two ends, one called the front and one called the rear of the queue, and you have a queue element. Queue can contain elements, and you have a length associated with the queue. In this example, it is having a length of 5, and you can also have an empty queue where the length is equal to 0. This is just created, no entries in the queue. So, this is a typical queue situation. Now, let us look at some basic features of queues. As I already told you, it is homogeneous. The elements inside the queue are not ordered. It is ordered only by the place in which it is, how it is entered, that is all. There is no implicit ordering of elements in the queue. Multiple occurrences of the same item, it is allowed, no problem. Okay. As I already told you, queue is a first in first out sequence of elements, and as I already told you, elements can be added only at one end, called the rear of the queue, and can be removed only from the other end, called the front of the queue. So, this is the basic concept. If you understand this, you have understood queues. Okay. So, the length of a queue is the number of element it contains. So, empty queue has a length of 0. Now, let us look at the difference between stacks and queues. So, this is the stack which you have already seen in the previous module. So, stack is the last in first out, and if you look at this, both the push and the pop operations, that is push is the insertion of stack and pop is the deletion from a stack, both happen at one end. Now, if you look at the queue on the other hand, it is follows the first in first out policy, and the queue the insertion here is called NQ, and it follows one end, and the deletion occurs from the other end. So, this is the difference between, just to compare between stack and queues. Now, as I already told you, the front will point to the front element, rear will point to the rear element. So, it is an ordered collection of data items, delete item from the front of the queue, insert item at the rear of the queue, it is an FIFO structure, just to summarize what the queue means. So, how do we work with queues? That is the next question that we have to answer. Up to now, we have understood the concept of queues, that it is an FIFO structure. It has two ends, one called the front and one called the rear, and you always delete from the front and insert in the rear. This is basically what we saw up to this point. Now, we are going to see how do we work with queues, what do we do with these queues. Okay. So, just like a data structure, any data structure, you will have a create a data structure, insert, check whether it is empty, delete, and so on. These operations do not change, but the definition of these operations from the different data structures changes. So, that is what we are going to see with respect to queues here. So, we know the conceptual idea of a queue that we have seen up to now. So, now we can use a set of operations. Okay. So, and but as before, from the ADT viewpoint, as of now, we are not bothered about how these operations are implemented. We are not bothered about that. Okay. So, let us look at the queue ADT. It has an implicit explicit linear ordering, that is, it comes in one particular order. Insertions and deletions or removals are performed individually, you do not do it together, one element at a time you do it, and there are no restrictions on the objects that can be inserted into the queue. Okay. So, that object has to be inserted at the back of the queue, that is the only condition that we have, and the object designated as the front of the queue is the object that was in the queue the longest. Okay, that is the definition of front. So, the front points to a element in the queue that has been in the queue the longest, that is what we are trying to say. And the remove operation removes the element from that particular front of the queue, that is the element that has been in the queue the longest is the one that is removed. Okay. Now, let us look at insertions. Insertion happen at the rear of the queue and removals from the front of the queue, which we have already seen. And what are the main queue operations? Now, let us define the queue operations. So, the first is NQ. You have to have an object and inserts the element O or the object O at the end of the queue. So, just why we are using the term object is that particular element can be of any description. okay. But whatever that is, that element will be inserted at the end of the queue, that is all we are going to say. And DQ, which removes and returns the element at the front of the queue. As in any deletion operation, either you can just delete the element or you can delete the element and return it. It depends on your definition of that particular operation, just like in any ADT. So, now let us look at the queue specification. So, you have to have some definitions that has to be provided by the user for you to specify a queue. So, what are these definitions? First is, what is the maximum number of elements that may be on the queue. So, that means maximum number of items or max items, we have to define this. And we have to also talk about what is the item type, what is the type of data that we want to insert into the queue. This is the next thing that we have to talk about. Now, so this is the queue specification that we have. And we have operations. Now, before I go to this operation, you will remember that in any ADT, the definition of the ADT along with the operations forms an ADT. If you have another set of operations, it is another ADT. That is still valid and still valid for QADT. Now, let us look at the operations. Here we are just listing all the operations. Depending on your application, you will choose that particular ADT along with, that particular queue along with the operations. So, some may have a subset of the operations, which we have already discussed a lot in the previous modules, but I just want to stress that again. But what we are trying to tell here is the list of operations that we are talking about. Okay. So, the first one is create an empty queue. This is a typical operation. Destroy a queue, that is remove all the elements from the queue. Determine whether a queue is empty or not. This is again a typical operation. Then add a new item to the queue. Now, here is where the difference comes. What happens? You can add only in one particular way, not like a normal list where you could have added anywhere, not like a stack where you add at the top. In the queue, the definition of where you can add an element or an item is fixed. Okay. Similarly, remove an item, which element or item can you remove, that is also fixed because of the definition of the concept of queues. So, that is there. And then retrieve an element, this also we have seen before. This is retrieve an item from that has been added. What you can retrieve will be the one that has been added first, but then when you retrieve it, either it could be deleted or you could just retrieve and show the element, the queue remains the same. This again, these operations we have already defined a number of times. So, now let us look at the operations in detail. So, you have create queue, which returns a new queue, that is how that new queue is defined, whether it is a list or an array or a linked list, we are not talking about now. When you call create queue, it will return an empty queue to you. So, when the empty queue is given to you, you will have the front and rear defined, that is what it means, and the locations where you want to put the elements. Then add queue, adds an element to the rear of a queue. You do not have to say where to add, it is automatically added to the rear of the queue. Is empty queue returns whether the queue is empty or not. This is a typical Boolean operation which returns true if it is empty and returns false if it is not empty. Then you have front queue, which returns the element at the front of the queue. Here now no deletion happens, it just returns the element at the front of the queue. Okay, this is just accessing the element. Again, this we have seen in a similar vein for stack. And delete queue deletes the element at the front of the queue. So, that is the idea here. So, front and delete are different in the sense delete removes the element and updates the pointer appropriately, while front queue returns the element, no change in the queue. Now, there are some auxiliary queue operations, these are the main operations. So, what are the main operations as we have seen? Create, then add, then you find out whether it is empty, delete and then access the front element. These are typical operations, a similar set of operations you will remember from stack also. Now, there are some auxiliary queue operations. What are the auxiliary queue operations? Front, it returns the element at the front without removing, which you have already seen. Size can give the number of elements that have been stored in the queue, this is also possible. Then is empty returns a Boolean, which you have already seen, and exceptions are there. This is typical again, execution of a DQ on an empty queue will always throw an empty queue exception. Okay, so, you cannot delete an element from a queue if it is empty. So, this is true for any data structure, list we have seen up to now, list, stack, now queue, this exception comes. Now, added to this you will remember there is an add thing. You can add an element if the maximum size is not exhausted, but that is implementation specific for array. This is true for again list, stacks and queues. Now just to summarize, these are the operations on the queue. DQ removes element from the front of the queue, NQ adds an element to the rear of the queue, first examines element at the front of the queue, is empty, determines whether the queue is empty, size determines the number of elements in the queue, and there is another operation which is given here. It depends on the application. It returns a string representation of the queue, which means the elements of the queue are returned as a string. It depends on the application that you want to use the queue for. So, the queue operation, let us look at how this is. So, the creation of an empty queue is can be represented like this: queue name, that means you want to access the queue, that is queue name. You have the queue operation. So, when you do the queue operation, an empty queue is created. Then the operation, determine whether a queue is empty. Now, let us look at what are the preconditions and what are the post conditions for these operations to occur. So, let us look at that. So, we are calling boolean is empty. So, it returns either true or false. Precondition, no precondition is there. Post condition, it returns true if the queue is empty, otherwise it will return false. So, this is the definition of a queue operation is empty. Now, let us look at the NQ operation. As you remember, the NQ operation inserts an element at the rear of the queue. Okay. So, where it is inserted is need not be defined, because it can be inserted only at the rear. So, that is the issue. So, now let us look at, now I have defined this particular NQ operation as a boolean operation. What does that mean? It does the operation, if the operation is successful, it will return a true value, else it will return a false value. This is not the only way in which you can define this operation. You can define it as a NQ alone with the item, with just no boolean value. But here we have chosen to define it like this. It is only just one way of defining, you can define it in many other ways also. So, let us first look at the original queue. Now, the original queue here which we have used contains 4 elements, 23, 44, 77 and 52, and front points to the first element and rear points to the last element that has been inserted. Okay. So, that is the original queue. Now, we want to do an insertion operation or an NQ operation. So, what do we want to do? We want to insert an element 40, and that is the data to be inserted, and the precondition for this NQ operation is there has to be a new item, otherwise you cannot do an insertion. So, the new item is the item to be added. Okay. So, once this is decided, we will call the NQ operation. When you call the NQ operation, you will call the NQ operation for the queue, original queue, and after the NQ operation, what happens? The front does not change, 40 has been added after rear, and rear is incremented. Now, here I am saying increment, it is changed. Okay. It depends on the implementation, whether it is incremented or whether the pointer points to other element and so on. But here rear changes. Okay. Now, so what is the post condition? If the insertion is successful, then the new item would be there found at the rear of the queue, and that is the back of the queue. Okay. That is the post condition. So, this is the NQ operation. Now, let us similarly define the DQ operation. So, the DQ operation deletes an element from where the only place from which it can delete is the front of the queue, that is fixed as before, where we can insert only at the rear. Now, again we are defining it as a boolean operation, not necessary as I told you before. So, what this boolean operation will give a true if deletion is possible, otherwise it will give a false value. So, again now when you call DQ, you have to of course give the queue name, which queue you want to do this operation on, and also the element here data item will contain the element that has been deleted. You need not define it like this, you can or need not. So, let us assume the original queue has again 23, 44, 77, 52 with 23 front pointing to the element position of 23 and rear pointing to the position of 52. Okay, let us assume that is the original queue. Precondition, there is no precondition. Okay. Now, let us assume you call the DQ condition. Now, what happens is the front element, that is 23, has been deleted and front has been updated. I will leave it as updated, not incremented, that depends on the implementation. So, it has been updated, rear does not change. So, this is the queue after the DQ operation has been done. And what is the post condition? If the queue is not empty, the item that was added to the queue earliest will be removed, in our case 23, However, if the queue is empty, that is there is no element in the queue, then deletion is impossible, and so the Boolean operation DQ will give a false value. So, this is the post condition and precondition for this DQ operation. Corresponding to this DQ operation, you have what is called a get front. Now, this retrieves the element or the item at the front of a queue. So, again we can define it as a Boolean operation where you have queue item type, and we have given a pointer to the front of the queue. There is no precondition. The post condition is if the queue is not empty, queue front will contain the element that was added to the queue the earliest. So, that is what will happen. So, this remember the queue remains the same, no deletion has happened, no updation of the pointers or anything of that sort. Only thing is you are accessing the front element of the queue. So, now let us look at some typical queue applications. What are the applications of queue? So, let us look at some real life examples. Waiting in line is a typical example. Waiting on hold for some technical support. So, this buffering is a typical concept. Here I will not explain it as buffering. Just waiting till something else happens is a typical example. And there are some particular applications related to computer science. Here we have threads. Thread is a typical application where queues are used. Then job scheduling, this is very important use of queues. Round robin algorithm for the CPU allocation. Similarly, for memory allocation you can have job scheduling. When you have memory allocation also there will be a queue used. There are some other type of queues also called priority queue. So, queue is an important data structure as far as computer science is concerned, especially for scheduling type of applications and buffering type of applications. We will go into that in detail when we talk about modules or applications. Then there are some direct application like access to shared resources. So, if you have a resource that is in demand, then obviously you will have to wait in a queue for that resource to be allocated to you, and that data structure where that is whether it is virtual or whether it is actual physical waiting, it is called for example, for the use of a printer it could be a queue. Multi-programming where different processes wait for the CPU time, again that is a queue. Of course, instead of just a queue you could give it priority and things like that. We are not talking about that here, but the jobs are waiting to be done, and that is first come. The first normal course of action, whoever has come first will be given first, or whichever process has come first will be given first. Computer networks, again there is lot of scheduling that is done for resources. Okay. Then OS, as we already discussed, job scheduling, CPU allocation, memory allocation, all places you do have this queue data structure needed in computing. Indirect application, it is used as auxiliary data structures for algorithms as a buffer. It is a typical use of queue is as a buffer, and also as component of other data structures. So, these are some of the very important applications of queues. Okay. Now, why do we use queues? The purpose of queue is to provide some form of buffering, but that buffering is not only for storage, it is also having a methodology that whoever has come first has to be serviced first. So, that buffering. Typical uses of queue in computer systems are process management, as I already told you, buffer between the fast computer and the slow printer. So, this queue data structure was used a lot when we had input output devices that were slow compared to the computer which is fast. So, that means there is a lag, and that lag is tackled by having a queue data structures and jobs being put in the queue and taken out of the queue in the first in first out manner. So, you can define a queue as also an access restricted list. So, there are many situations when there is a speed mismatch. Okay. So, in these type of applications queues are used. So, we are just looking at it from another viewpoint. So, a service is there which has to service more than one client, and the arrival rate of the clients is much more than the service rate. So, any situation where such a context occurs, we use a queue. So, ticket counter also you can look at that. The ticket counter, the service is offered by the ticket person issuing the ticket, but if the customers come in the same rate at which he is issuing tickets, there is no problem, there is no need of a queue. But since he is issuing tickets at a slower rate than the people coming in, then there is a need for a queue. So, that is the example. Then again a producer and a consumer operating at different speeds. So, I have a producer consumer problem. where I have people producing things, but the consumers consuming it as a slower speed, then these products have to be again wait in a queue. Input devices and programs and outputs and so on. So, in computing again, for any kind of problem involving FIFO, we need the queue. Very important data structure as far as computing is concerned. Typical examples are printer queue, keyboard input buffer, GU event queue. This is very important. Click on buttons, menu items, all these when you click on, this is always maintained in a queue for you, so that as one is serviced, the next item on the queue is taken and then it is serviced and so on. Encoding of messages is another important and interesting application of queue, which we will be seeing in detail as we go along in the further modules. Okay. In simulation studies, where there is where you want to the goal is to reduce the waiting times. So, for example, you want to optimize the flow of traffic at a traffic light, then in that situation also you do tend to use queues. Determine the number of cashiers to have on duty at a grocery store at different times of the day. How do you do this? See, if you put too many cashiers, then when the number of customers is less, they are all wasting their time. So, what you can do is you can take an average length of the queue at different periods of day at the grocery store and put as many cashiers as you want depending upon the length of the queue. You would have seen that when you go for what is that, check-in at the airport counter, suddenly there will be only 2 people servicing, and then the queue gets longer, and as the queue gets longer, what happens, they put in more service counters. This you would have seen as you wait in the airport. That is what a good airline would do for its customer. So, now let us look at what we have spoken about now. We basically discussed the concept of a queue from different angles, and we looked at queue as an ADT. We looked at the FIFO principle, the concept of that it had 2 ends, and the first the element that is longest in the queue is removed first, and that was the concept of the queue. Then we explained what the queue ADT was, what are the requirements of a queue ADT, and then we looked at the operations. So, the operations that are done on queue is similar to the operation we saw on the other 2 important data structures we have seen up to now, list and stacks. However, the definition of what is add and delete is what is changed, or in other words, from queue's viewpoint, NQ and DQ. And then we discussed some possible applications of queue, especially in the area of computing. We did not look at application per se, but what we looked at is what are the situations where queue can be used in general. We will be going to the applications in modules which we will be discussing later. So, thank you.